Hi everyone, my name is Ray Lee and currently a research fellow at University of Warwick. And today I will give a short research update on my recent work with Professor Xiaowei Zhang at the Warwick. Specifically, I will briefly introduce the recent progress of our research on wind turbine surface anomaly detection using a context-aware transformer framework. Operations and maintenance is a major contributor to the total cost of wind farms, accounting for a significant proportion of the levelized cost. Because turbines operate in harsh outdoor environments, surface anomalies such as cracks, wear, and dirt accumulation are very common. Traditional inspection methods can be slow, labor-intensive, and sometimes difficult to deploy, especially for large or remote turbines. This is where UAVs become very useful. UAVs can capture high-resolution data efficiently, even in complex environments, and offer a safer and more flexible alternative to manual or ground-based inspection. In this work, we propose a context-aware detection transformer for detecting surface anomalies on different turbine components, including blades, rotors, towers, and nacelles. At the moment, YOLO-based models are still widely used in turbine anomaly detection because they provide a good balance between speed and accuracy. However, in practice, they often struggle with small, irregularly shaped, or virtually subtle defects, which are common in real wind turbine inspection scenarios. To address this limitation, we built a transformer-based detection framework and introduced a novel context-aware attention mechanism specifically designed for this task. The key idea is that instead of relying only on local appearance, the model can better use surrounding contextual information when identifying defects. This helps the detector focus more effectively on challenging anomalies that may be missed by conventional approaches. This slide shows the quantitative comparison in terms of mean average precision over 100 training epochs. We compare our method against transformer baseline and a range of zero models from different generations. The main takeaway is that the transformer-based approaches show a clearer advantage in convergence behavior, and our method achieves stronger overall detection performance. In other words, the model not only learns effectively, but also reaches a better level of accuracy for this application. This suggests that incorporating context-aware attention is beneficial for wind turbine anomaly detection, especially when the visual patterns are complex. Here, we show a qualitative example on a turbine hub with multiple small and clustered surface damages. This is a challenging case because the defects are close to each other and easy to be missed. As shown in the comparison, the YOLO-based models and the baseline transformer fail to detect all of the damaged instances, especially the one in the upper left region. By contrast, our method successfully detects all ground truth objects. This example highlights that our method is more sensitive and more robust when handling things with multiple small targets. This is another challenging example, involving a subtle low-contrast dirt line together with a small high-contrast damage spot. These mixed visibility cases are particularly difficult because one target is visually obvious, while the others is much less distinct. Again, our method correctly localized both defects and produced a tighter bounding box for the subtle dirt region. This indicates that the model is not only good at detecting obvious damage, but also better at identifying weak or ambiguous anomaly signals. To conclude, this slide summarizes the research outputs produced under the Supergen ORE Impact Hub. Thank you very much for your listening.